Coulomb's law is the law that deals with two charges at a distance. Both charges are, if both charges are the same, they repel each other, and if they're different, they attract. Um, you don't really need to worry about the math for it, like positive and negative, as long as you know this, because the equation doesn't change for either circumstance. The equation applies to both charged particles, such as an entire atom acting upon another atom, or it applies to not subatomic, but protons and electrons. If a proton and electron could not directly adhere to one another, like if there was a particle nearby and it was not acting upon the other particle, but there was a very slight force between the proton in the nucleus of one particle and the electron, the valence electron in the shell of the other particle, there would be a very weak force present, and you can use the equation to determine that small force or the force between the entire two particles. Gravity is basically the same thing, but Newton's law for gravity is not very accurate.
Gravitational force versus electrostatic force. Two of the fundamental forces are gravity and electrostatic force. Here are two equations that determine gravity and electrostatic force between two objects. In these equations, G and K represent constants. M sub 1 and M sub 2 represent the masses of the two objects, and Q sub 1 and Q sub 2 represent the charges of the two objects. Both R and D represent the distance between the centers of the two objects. As you can see, there are some obvious similarities between the two equations. For instance, both equations are over the square of the distance between the particles. This is because both forces decrease exponentially as distance between the objects increases. This means that, as long as both objects have mass or charge, there will always be a force between them as they move farther apart, even though it may be very small. This also means that as they move closer to zero's distance, which is impossible, the force goes to infinity. Another similarity we can notice is that the top is a product of either the mass or charges of the two particles and a constant. This means that the force increases exponentially as the masses or charges increase. This also brings up a couple of main differences. In order for an object to exist, it must have mass, but an object does not need a charge to exist. This means that as long as the objects have mass, and they must, there will be a gravitational force between them. This is not true of electric force. If either of the objects has a charge of 0, then there is no electric force between them. Another difference is that electric force can be negative. Because we only work with objects with positive mass, there can only ever be positive gravitational force. But because charges can be positive or negative, electric force can likewise be positive or negative. Because of this trait, gravity is known as a monopole force, and electrostatics is a dipole force. As of research today, scientists are unsure of this correlation between these forces. As research is put into studying dark matter and gravitomagnetism, a link may someday be found between gravity and electric force, but today it still remains a mystery.
The four basic forces of the universe are gravity, the strong force, the weak force, and electromagnetism. Gravity is the natural attraction of all objects with mass to all other objects with mass. The formula for it is the mass of object 1 times the mass of object 2 times the gravitational constant divided by the distance between the two squared, which is also very similar to the formula for electromagnetism, but it more closely applies to the formula F equals ma. Since all things are gravitationally attracted at the same acceleration, dependent upon the mass of the system, the mass of each individual object determines the amount of force that gravity applies on it, and that gravity has to apply on it to get it to move. And yeah, that's why when you drop two things that have different mass, they both accelerate the same, but they both have a different force, because they have different masses. So, yeah. And gravity is the weakest force that there is. The next force is the weak force. And the weak force is basically what determines whether or not something will radioactively decay. And it is it's what transforms neutrons into protons, and it is by far the weakest force. Or not the weakest force, sorry. It is stronger than gravity, right? And that's the only thing it's stronger than. But the only reason that gravity still works, even though the weak force is acting upon pretty much everything, is because the Earth is so massive that the amount of gravity that it can exert is still greater than the amount of weak force, the amount of force that weak force can exert. Now, the weak force is what basically ejects electrons from neutrons to make them into protons. The next on the scale is electromagnetism, which is not quite the strongest force. The strong force is the only force stronger than electromagnetism. It will interact between two things that have an opposite charge, or any two things with a charge. It will repel like charges, and it will attract different charges.
Aside from extremely small things like atoms and such, the equation also works for, like, if you could have a very negatively charged balloon and a very positively charged balloon, they will interact according to this law. It will probably be more difficult to see because, as we're on Earth, the gravitational force is the weakest force, but Earth is very massive, so it would overpower the two forces unless they were in close contact. There are many similarities between the Coulomb's law equation and the gravitational equation because they're basically the same equation, except gravitational equation comes from Newton, and when Einstein's theory of relativity was published, we noticed that his equation is only accurate up to a point, whereas Coulomb's law is accurate completely as far as we know. There is no issue with it that we are currently aware of.
The strong force is the strongest force, and it is only affects within the length of a femtometer, which is insanely small. But it is the strongest of all forces, and basically holds particles and atoms and stuff together, which is kind of cool. So, yeah, those are the four fundamental forces. These four forces are the only fundamental forces that we currently know of. There are many differences, like in the forces, like how they act, what they act on. But they're all forces that exist in nature.